Hello, I'm Nathaniel, and today we will now do question 6 of Step 2, 2021. So, we have the trace and the determinant. The determinant is the one that you might have encountered. The trace is, well, another measure. So, trace of m squared is, well, before we calculate trace, let's calculate m squared. It equals, using the multiplication formula, a squared plus bc, ab plus bd, AC plus CD, D squared plus BC. And then, if the determinant is 1, then you could just factor A plus D, yes, A plus D, throughout the whole matrix. Ain't it interesting? And just for fun, we're going to determine whether the determinant is 1. So we have A squared minus AD minus 1. So 1 is AD minus BC. So AD minus BC, and then we have D squared plus AD again minus 1. A plus D B, A plus D C. And since the determinant is 1, we have A plus D M minus I. That is an important formula when you're getting into the group of matrices with determinant 1. I trust you. It's called the special linear group of 2x2 matrices over the integers. Please go look that up. It's a quite an interesting topic about group theory. So, trace of m squared, as we have seen, is a squared plus bc plus d squared plus bc, because that's the entries on the diagonal. It equals to trace of m squared minus 2 determinant m, because we will have a squared plus 2ad plus d squared minus 2ad plus 2bc. That's it. Now, prove that m squared equals to I, but then this, well, as far as I know, there is only one matrix. Yes, one matrix with satisfying these conditions. It is 0, 1, 1, 0. The trace of m equals to 0 and determinant m equals to -1. I might tell you, but in your opinion, but can you prove it's the only matrix? Well, you pedants, you can figure out the proof yourself using the actual formula. But I'm just telling you, for example, that you need to remember this matrix because you never know when it will come up. And besides, this matrix has a sneaky habit of pretending to be idempotent. You never know why. And try figuring out when this sneaky matrix just pretends to be idempotent. Alright? So, use part 2 to prove this. So, if m4 equals to I, m squared equals obviously plus minus I, because determinant of minus I is 1 and determinant of plus I is 1, and determinant of this silly matrix equals to -1. Find necessary and sufficient conditions so that m to the power of 4 is -I. So we will now have trace of m squared equals to -2. Then -2 equals to the trace of m squared minus 2 determinant m. And then, since determinant of m is 1, well, obviously, otherwise how can it be -1? So trace of m equals to 0. However, if we can prove that trace of m squared is 0, and then the trace of m squared minus 2 determinant m. So if determinant m equals to 1, trace of m equals to the square root of 2. But if determinant m is -1, then you can't find trace of m. So trace of m is square root of 2 and determinant m is 1. So now for the last part. So if m to the power of 8 is I, so that means either m squared equals to I, m squared equals to the -I, or m to the power of 4 equals to -I. So I can give you another matrix besides this silly matrix which pretends to be idempotent. There is another one of these weird matrices which doesn't prove to be idempotent but still a weird matrix nonetheless. it is this matrix, often called S in the group theory community. When you take it to the power of 4, you get I, which satisfies the m squared equals to minus I condition here. Well, see you in another step video.